So in terms of paper analysis, on average we find that in JEE Main there are about 2 questions at least from this chapter, and in JEE Advanced there are generally at least on average 2 questions. But if you look at last year in 2018, there were actually 4 questions from this chapter. Okay, and the most common concepts that occur, the most frequent concepts are rolling, conservation of angular momentum, and moment of inertia. You can on average expect at least 1 question purely on moment of inertia in JEE Main every year. So in this problem, we have a sphere that is projected up an inclined plane of some angle theta. Say this is your sphere. It's given up an initial velocity of v node, and the angular velocity, initial angular velocity, is 0. The coefficient of friction is given to be tan theta. The question asks us to find the total time of rise of the sphere. That is the time taken for the sphere to basically reach its maximum position, its maximum height. Okay, how do we do that? First, so as you can know, this is, obviously you would have guessed, it's obviously a rolling problem. There is some amount of rolling that's going to happen. And it's not, obviously you won't get pure rolling, right? It won't be completely pure rolling because initially it has 0 angular speed, which means that friction is going to, or rather it'll slip initially, and then it'll reach a position, it'll slip in such a way that it'll start rolling, but then after a point, it'll reach a point where there'll be pure rolling. Now, so that means we can split this into 2 motions. One where when there is no pure rolling, and then when it reaches a point where there is pure rolling. So let's say that the time taken for the first case, when there is no pure rolling, is t1, and the time taken for the second case, when it reaches pure rolling and then reaches the highest point, is t2. So there are 2 motions. Now first, let's talk about the first case, when there is no pure rolling. What do we do? Let's first draw this free body diagram to make things simple. So there is, of course, gravity acting in the downward direction, but then I can split it into its components. One over here, which will be mg cos theta, and one over here, mg sin theta. And what's important to know is remove the original force, because many times we end up making the mistake of splitting it into the components and keeping the original force as well. So remove the original gravity force. So these are the 2 forces. And of course, there is no friction, which will act, okay, let me do it over here, will act in this direction, right? And that, let's say, is some F. And this friction will be kinetic. So let's call it Fk. It'll be kinetic because there is going to be slipping. It's not going to be static friction. Okay? Any other forces, of course, there will be normal force as well in this direction. Right? Now, so the first thing I'm going to do is I'm going to calculate the deceleration of this ball as it's moving, as it's doing, non-pure rolling. And to do that, I need to find the net forces acting on it, right? So in this case, of course, we forget about the motion. Since there is no motion along the perpendicular, we have only a motion along the surface of the ramp. So the forces along that direction are friction and gravity. So the net force F will be equal to gravity. But then what is Fk equal to? That should be equal to nu into n plus mg sin theta, right? And n should be equal to mg cos theta. So we have F is equal to tan theta into mg cos theta plus mg sin theta. And this should be equal to sin theta by cos theta we finally get 2 mg into sine theta. So this is the net force acting on it, right? Now what will be the acceleration here? The acceleration will be the net force divided by the mass. So A will be equal to 2 mg sine theta divided by m. It's important to note here that A is the deceleration, it's not the acceleration, right? Or rather, I mean, in the sense both are the same. It's just that since the force is basically opposing movement, right? We obviously know that the ball or the sphere is going to decelerate, and so therefore the magnitude of the deceleration should be equal to 2 mg sine theta by m, which gives us 2g sine theta. Okay, now what? Now let's look at the torque, the net torque acting on this on the sphere. Right? Since the only force that's not acting on the center of mass is the force of friction, then the net torque will be only equal to F of k into r. Right? That's the net magnitude of the torque, and that should be equal to I alpha. Correct? I, of course, being moment of inertia, etc. So Fk into R will be equal to mg sine theta into R should be equal to 2 by 5 mr squared, which is the moment of inertia of a sphere, into alpha. Now, if we simplify this, we get alpha is equal to 5 by 2 g sine theta by r. Right? And this is your angular acceleration. Also, basically, this will be the deceleration, right? So the magnitude of your angular acceleration will be equal to 5 by 2 into g sine theta by r. So now that we have the deceleration and the angular acceleration, and we know that the time taken for it to reach pure rolling, we have assumed is t1, right? So this means that let's assume that at pure rolling, just when it reaches pure rolling, it has a speed of v, and it has an omega, or angular speed of omega. Okay, these are the two values. And we know that because it's reached pure rolling at that point, we know that v should be equal to omega r. Right? So let's first calculate v and omega. What will be v equal to? For that, we're going to use our laws of kinematics. Okay, our simple kinematic equations. So v should be equal to v naught minus at, right? So that means that v should be equal to v naught minus a, which we calculated, 2g sine theta into t1. Right? This should be equal to the value of v, and omega should be equal to 0 plus alpha t1. Right? Because the initial omega is 0, the final omega is what we have to find. So that will be equal to 5 by 2 g sine theta divided by r into t1. Now this, therefore, since v should be equal to omega r, we can directly write that v naught minus 2g sine theta t1 should be equal to 5 by 2 t1 into r. Okay, cool. So then this gets cancelled. Then finally, so we get t1 will be equal to 2v0 by 9g sine theta. And this is the value, this is basically the time that it will take in order to reach a state of pure rolling. So we've solved the first half of the problem. Now comes the second half. Now we have to calculate the time it will take for it to reach the maximum height. From here, it should reach the maximum height, right? What will that time be? a ramp like this of some theta, and if you have a sphere or any body rolling like this and is rolling downward, we know that the acceleration of this rolling body A is given by g sine theta by plus ICM by mr squared. Right? Now, the thing is, the same formula is also applicable to this case, the case where the body is rolling up. It's the same thing because it's symmetric, right? The time that it takes to go up will be equal to the time that it takes to come down. So the same acceleration formula can be used over here. The only difference being this will give us the deceleration. Okay, so if we do that, the value of ICM over here, I get g sine theta by 1 plus r squared. So this thing gets cancelled. So finally we get 5 by 7 g sine theta. So this is the value of the magnitude of the retardation after pure rolling starts. So for that, let's calculate the speed at that point. So v, which is the speed just after or just before at that point when pure rolling starts, that will be equal to v, which is equal to v naught minus 2g sine theta into t1, right? Because the acceleration is 2g, deceleration we found is 2g sine theta. Now the same value of t1 that we found over here, I'm going to substitute over here. So that is 2v naught by 9g sine theta. So this will be equal to v naught minus 2g sine theta into 2v naught by 9g sine theta. If you simplify this, you'll finally get sine theta gets cancelled, g gets cancelled, v naught by 9, which becomes 5 v naught by 9. Right? So this is the speed at that point, just when pure rolling starts. Now we also know the deceleration. So if the time taken for it to reach the maximum point is t2, then 0 should be equal to into t2, which means that if you let's simplify this, we get 5 by 7 is equal to 5 by 9 v naught. So t2 equals 7 by 9 v naught by g sine theta. Yeah, 7 by 9 v naught by g sine theta. Now we have the values of t1 and t2. So the net time taken should just be the sum of t1 plus t2. So let's call it capital T. Capital T should be equal to 2 by plus 7 v naught by 9g sine theta, which gives us 9 v naught by 9g sine theta. So basically v naught by g sine theta. So here we have another interesting problem where there are two plates, 1 and 2. They're called 1 and 2. So here you have plate 1 and plate 2. Plate 1 is moving in this direction with a speed of v, and plate 2 is moving in this direction with the speed of 2v. The question says we need to find the kinetic energy of the whole system. That is the plates and this disk. Oh, it's a sphere, and the plates and this sphere as well. Now, what else is given? Given the masses of each of these bodies is given. All of them is given to be M, and M. Radius is not given. We'll just assume it to be R. Okay. Now, what do we do? How do we go about solving this problem? Obviously, getting the kinetic energy of the first, that is the plates, is simple. It's just going to be half mv squared, so that we can easily find. But how will you find the kinetic energy of the sphere? Now that's the interesting bit, because it's rotating, obviously, but about what? Is it rotating about the center? No. So let's find out where exactly it's rotating. So we know that the bottommost point of the sphere is moving in this direction because it's in contact with the bottommost plate, and we've been told that there is no slipping. So that with the speed of 2v, and the topmost point is moving in this direction with the speed of v. Okay. Now, since both these points are a part of the same body itself, we can assume that the speeds, now if I draw a line like this that cuts through the sphere like this, I can assume that the speeds are varying linearly, right? It's linearly starting from 2v, and then it keeps reducing till it reaches a point 0, and then it starts increasing in the other direction till it reaches a point v. So if I had to represent it in some way, it'll be like this, and these are the corresponding points, something like this. Yeah. So this point over here will basically be the center. Let's call this O. Will be this point O, right? Now, so we can see that at some point over here, let's call it C. At some point C, the speed is becoming 0. Right? It's basically starting with 2v in this direction, it's reducing slowly, becoming 0, and then increasing v in the opposite direction. Now, why is this point C important? Because we need to find the instantaneous point about which this body is rotating. And we know that the instantaneous axis of rotation with respect to the ground always passes through the point which is at rest instantaneously with respect to the ground. Right? So that's why we need to find that point that is having 0 speed with respect to ground, and we can assume that the whole body is rotating about that point. Okay, so that's why I'm doing this. So that we need to find that point about where the speed is 0. So if I do that, I can just use similar triangles. Let's assume that this distance is y, right? Then we can see here, just because of similarity, that y by v should be equal to 2r minus y by 2v, right? Now, if I substitute, I find that y will be then equal to y should be equal to 2y3r. So this tells us at which point, the point at which the body will have 0 speed, and that will be the instantaneous axis of rotation. Again, the reason I'm finding that is because using that instantaneous axis of rotation, now I can calculate the kinetic energy of the sphere, right? So to do that, I just need to find basically the moment of inertia of the sphere about that point, and of course the omega, because kinetic energy is half I omega squared. Let's call it Ke of the sphere will be equal to half IC omega c squared, where IC is the moment of inertia of the sphere about that point, and omega c is that's the angular speed of the body about that point. Now let's go one by one. Let's find omega. Omega about that point will be equal to v by y, right? Because if you look at the point So this is your C, and this point is, let's say, some P. Now the point P is moving with a speed of V, right? And the distance from the point, which is the instantaneous axis of rotation C, is Y. So its omega will be nothing but V by Y, right? So then omega will be V by Y, and that will be equal to 3V by 2R. If I substitute the value of Y equals 2 by 3R, right? Now this is your value of omega. Now I need to find IC. How will we do that? Well, we can use parallel axis theorem, because we know that the moment of inertia of a sphere about its center, about the center of mass, is 2 by 5 mr squared. So this will be 2 by 5 mr squared plus m into this distance. Oh, cool. That will be OC. So OC the whole squared. Correct? This is the value of IC. If I calculate that, I get 2 by 5 mr squared plus m into what is OC. OC will be equal to R minus 2 by 3R the whole squared, right? Because Y is the other value, right? So this value is Y, so OC will be R minus 2 by 3R. Now if I do this, I get 2 by 5 mr squared plus m into r squared by 9. Find the value, I get 45 plus 5 into mr squared, which will be equal to 23 by 45 into mr squared. Is that correct? Yes, it is. Now the value of kinetic energy, that is just the rotational, just the kinetic energy of the sphere, will be half into 23 by 45 mr squared into omega c squared, and omega c we already found, which is 3 by 2 squared. Now if we simplify this, we finally get 23 by 40 into mv squared. So the total kinetic energy, this is just the kinetic energy of the sphere. The total kinetic energy will just be the sum of all three kinetic energies, right? So Ke total will be equal to half mv squared plus half m into 2v the whole squared. That's the kinetic energy of the bottom plate, plus 23 by 40 mv squared. If you calculate that, we finally get this answer to be 123 by 40 mv squared. So in this question, we have a man who's standing on top of a turntable, and this turntable is mounted on top of a vertical axis. Okay, he has a mass, of course, which is 100 kgs. The moment of inertia of the turntable is given to us, 4000 kg meter squared. The man starts walking in the anti-clockwise direction, the counterclockwise direction. So if you from viewed on top, basically, let's say in this direction, like this, he starts walking with a speed of 1 meter per second relative to the earth. Okay, this is relative to the earth. Now, the first question is, with what angular velocity and in what direction does the turntable rotate? Okay, First of all, will the turntable rotate? It should, right? Because the turntable is placed on a frictionless shaft, which means that the net external force, besides the normal force, there is no net external torque that's coming from outside, which means that if the man starts walking, he'll be applying a friction force on the turntable, right? Because it'll be friction, and that friction will be internal, but for the turntable it'll be an external force, and that will rotate it therefore in the opposite direction. Or you can say that if you take the man and the turntable together as a system, there is no net external torque that's coming. So therefore, to make sure the net angular momentum is the same, the turntable has to rotate in the opposite direction. Now initially, since both bodies are not moving, the net angular momentum is 0. So the final angular momentum should then, what will that be? Let's find out. Well, let's say L man. What is the angular momentum of the man? Well, that will be I man into omega man plus the angular momentum of the table, right? So let's say that will be equal to I table and omega table. Right? This is the net angular momentum. Now, what will be the moment of inertia of the man? Well, that we know has to be equal to mr squared. So 100 into the radius is given to be 2 meters. Into omega m. So what will be his angular speed? Well, he's moving with a speed of 1 meter per second. So his angular speed should be, well, if he's moving like that, then his speed should be v by r, right? So it will be 1 by r, which means 1 by 2. Omega m will be 1 by 2. Now plus, this should be equal to IT, which is the moment of inertia of the turntable, which is given to be 4000 into omega t, and this is what we need to find, right? The angular speed of the turntable. Now this has to be equal to 0 because the initial angular momentum is 0, right? So let's just rearrange and find this value. So we get, this gets cancelled. Minus 1 by 20, right? So we finally get minus 1 by 20 radians per second. Okay, so what does this tell us? This tells us that the omega will be negative, which makes sense. We already said that, right? It has to be, now if he's moving in the counterclockwise direction, then the turntable has to move in the clockwise direction, but the magnitude of omega will be 1 by 20. Now the second part to the question is this. Now the question says, if the man reached his initial position on the turntable, that is, he started walking with the same speed, and the turntable moved in the opposite direction, well, then finally he reached his initial position on the turntable, which means that with respect to the turntable, he completed one full circle. If that is true, then what is the angle that the turntable rotates by with respect to the ground? Okay, so this is what the question is asking. So how do we do that? Well, basically the question is telling us that if let me use another color. So if theta, that is the angle that the man covers with respect to the turntable, so that's why theta mt, if that is equal to 2 pi, right, then the question is asking what is theta t equal to, right? The angle that the turntable covers with respect to the ground, right? Now, how do we do that? Well, we know that theta mt should, if this is equal to 2 pi, that's fine, but that is also equal to theta m minus theta t, right? Which is the angle that the man covers with respect to the ground minus the angle that the turntable covers with respect to the ground. We are simply using the simple equation of relative motion, right? So if this is true, then how else will I know? But I know, what do I know? I know omega m and omega t. Correct? Omega t I just calculated, omega m is given to me. Omega m is the angular speed of the man with respect to the ground, and omega t is what we just calculated. Then I can write theta m in terms of this, right? So I'll write theta m as omega m into t, right? This t being time taken, minus omega t, right, into t. Correct? Because omega mt will give me theta, and omega tt will again give me theta t. Correct? Okay. So then let me calculate the time taken, and this should be equal to 2 pi. This is something that we already know. This is what the question gives us. So what we do is we're going to calculate this time taken. Okay. So let's substitute the values. Omega m. What is omega m equal to? Omega m will be equal to 1 by 2, right? 1 for the speed that the man covers, and 2, which is the radius, into t, minus omega t is something we already calculated, which is minus 1 by 20, right? Into t is equal to 2 pi. So I get t by 2 plus t by 20 is equal to 2 pi. Okay. Now let me simplify. This becomes 10t plus 1, so that becomes 11t is equal to 2 pi. This implies that t should be equal to 40 pi by 11. This is the value of time taken, basically seconds, right? But the question says we have to find the angle covered by the turntable with respect to the ground. How do we do that? Well, we know omega, right? We already calculated omega. Omega t is what? Minus 1 by 20 radians per second. So theta t should be equal to time taken into omega t, which is 40 pi by 11 into minus 1 by 20. Okay. So we get minus 2 pi by 11. So the angle covered by the turntable with respect to ground will be minus 2 pi by 11 when the man reaches the same point on the turntable again. Now the last part of the question says, what will be the angle moved by the turntable if the man comes back to his initial position with respect to the ground? Now what do we do for that? Well, that means that if he's come to his initial position with respect to ground, then this means that theta m, which is the angle that the man covers with respect to the ground, should be equal to 2 pi. Right? And we know that omega m is equal to 1 by 2 radians per second. Then the time taken for the man to complete theta should be equal to t, let's say is the time taken. The time taken for him to complete 2 pi with respect to the ground should be equal to theta m by omega m, which is 2 pi by 1 by 2 or 4 pi. Right? 4 pi seconds. Now, this is the time taken. Now, the question says, what should how much should the turntable have turned? Well, for that, we know the time taken, and we also know omega t, which is equal to minus 1 by 20. right? So theta t should be equal to omega t into the time taken, right? Which is equal to minus 1 by 20 into the time taken, which is 4 pi. So minus pi by 5. Our answer is minus pi by 5. So the angle or the turntable would have turned through an angle of pi by 5 in the same time. So here we have a match the following question where we have different cases and different options. Let's first analyze the first case. We have some sort of circular object. From the options, we can see that it's either a ring or a sphere. It can be one of the two. And this object has speed in this direction and also omega in this direction. Let's say this omega, as we can see, is in the counterclockwise direction. So let's assume this omega is positive. Okay, and we know that omega is equal to 2v by r. This is given to us. Now the question is, we need to find if once rolling without slipping begins, once it starts doing pure rolling, will the center of mass, the velocity of center of mass, be in the right side or in the left side? Will it move to the left side or to the right side? That's what we need to find out. How will you do that? See, we can see in this case, first of all, let's go one by case. We can see one by one. In this case, we can see that omega is equal to 2v by r, which means that it is greater than v by r. So intuitively you'll know that this ring is rotating in this direction with a greater omega than that is required for pure rolling. The important thing is that the friction force will always act at the lowermost point, at this point, right? It'll either be in this direction or in this direction, but it'll be at the lowermost point, which means that the torque, the net torque of this about that point will be 0 because there's no other force acting, right? In the horizontal direction, of course. So the net torque about this point of contact with respect to the ground will be 0. And therefore, we can conserve angular momentum. The angular momentum about that point before pure rolling starts and after pure rolling starts will be the same. Okay, and this is going to help us find out if the velocity of center of mass will be towards the left or to the right. Let me show you how. So first, let's calculate the initial angular momentum. So let's say Li for this case. So let's first assume it's a ring. Okay, so if we're going to assume that clockwise rotation, if it's going to rotate, clockwise rotation is going to cause negative angular momentum, then I omega we can see about this point, about that is in the anti-clockwise direction, correct? So therefore anti-clockwise will be positive, so therefore this will be mr squared into omega. Angular momentum of the center of mass with respect to the point of contact will be again in the anti-clockwise direction, so therefore it will be plus mv into r here. So the initial angular momentum will be equal to mr square omega plus mvr. Okay, now so this will be equal to mr squared into 2v by r plus mvr, which will give us 3 mvr. And this is positive. Center of mass should be moving in the left direction. Only then it will be positive, right? So this tells us that because this is positive, if this was a ring, then the center of mass will move towards the left. Will continue to move towards the left. Okay. Now, what if instead of a ring we had a sphere? Because that's the other option. So let me say let's calculate the initial angular momentum if this body was a sphere. Well, then that will be 2 by 5 mr squared omega plus mvr, correct? Yes. And this should be equal to 2 by 5 mr squared into 2v by r plus r. Which gives us 9 by 5 mvr. But honestly, from just by the previous, reasoning, you should realize that calculating the angular momentum doesn't really matter. All that matters is if it is positive or negative. So as we can see over here, we find that again in this case the initial angular momentum is positive, and just by the same reasoning, if the initial angular momentum is positive, then the final angular momentum after rolling starts also has to be positive, and therefore the angular momentum of the center of mass with respect to the point of contact should also be positive, which means that the center of mass should be moving towards the left. So the correct options for that matches with option 1 will obviously be A and B. We'll have A and B. So now that we know the concept, I'll just quickly go through the different options. All right. So what is the next option? So in the second option, we have another body like this, moving the speed v and an omega in the opposite direction, like this. So this means that omega is negative, right? Omega equals minus 2v by r. Okay. Now, what is the total? Let's calculate the initial angular momentum if it's a ring. Now, if it was a ring, Li will be equal to m r squared into omega, which is, plus Vr. This will be equal to mr squared into minus 2v by r, right? Plus mvr. This will be minus finally we get minus mvr. That is the initial angular momentum about the point of contact. What is important is that this is negative, which means that the net angular momentum after rolling start should also be negative. Therefore, the body should, or the point of contact, the center of mass should be moving towards the right. Right? Okay. So if this was a ring, the center of mass will be moving towards the right. So the first option that matches with that is option number C. Now, if this were a sphere, what will be the initial angular momentum? We'll get 2 by 5 mr squared into minus 2v by r plus mvr. Okay, and that will be equal to minus 4 by 5 plus mvr, which will be equal to 1 by 5 mvr. But then again, what matters is that this net angular momentum is positive, and therefore, just by the previous reasoning, that the center of mass should move towards the left. So the option that matches with this is, so we have B. So the right options that match with option number 2 is B and C. So let's quickly go to the next option. The option number 3 says omega is equal to plus v by 2r, right, in the counterclockwise direction. Now, if this was a ring, Li will be equal to m r squared into plus omega, so v by 2r plus mvr, correct? Now, without even calculating all this, we can see that this is positive, which means that after rolling starts, the body should move, or the ring should move towards the left, right? So the option that matches with this is VSM is towards the left in the case of uniform ring, so option A. Now, if this were a sphere, then it would be 2 by 5 mr squared into plus v by 2r plus mvr. Again, this is positive, which means that again the body should move towards the left. So if this were a sphere, then we have option B that matches with this. Okay, and the last case, we have omega equals minus v by 2r. Let's quickly calculate. If it's a ring, Li will be mr squared into minus v by 2r plus mvr, which should be equal to mvr minus mvr by 2, so we get positive mvr by 2, which is positive. So this, then the velocity of center of mass will be to the left. So if it's a ring, it will be towards the left. So option A matches with this case. Now, if it were a sphere, then we have 2 by 5 mr squared into minus v by 2r plus mvr. This should be equal to mvr minus 1 by 5 mvr. Correct. That should be equal to 4 by 5 mvr. Again, positive. This means that if it's a sphere, also center of mass will move towards the left, and you can see that B matches with this case. So in this problem, we have a ball of mass m moving with a speed v. It collides with a rod again of mass m and length L. The question also says that after the collision, the ball sticks. So let's draw a case after collision here. This, let's say, is the rod and the ball. After collision, the ball sticks to the rod. We need to find the speed of the ball after collision. Okay, how do we do this? Well, let's assume that the ball after collision moves with an angular speed of omega, right, in this direction after collision, and that the center of mass of the rod moves with some speed VCM. The center of mass VCM over here is the center of mass of the rod, not of the system, it's the center mass of the rod. So let's conserve momentum first. The initial momentum will be equal to mv, right? And the final momentum after collision will be equal to the momentum of the ball plus the momentum of the rod. Now, what will be the momentum of the rod, of the ball? The ball will be m, which is the mass of the ball, into its speed. Its speed will be VCM plus omega L by 2. Right? Because omega L by 2 will be its speed with respect to the rod. So its net speed with respect to the ground will be VCM plus omega L by 2. Right? So this will be the speed of the ball after collision with respect to the ground into m will give you the momentum of the ball plus the momentum of the rod will be m into VCM. Right? Okay. Now if I calculate this, m will get cancelled. We get V is equal to VCM. There's 2 VCM plus omega L by 2. Okay, so we get 2V is equal to 4 VCM plus omega L. So this is one equation. So now for the second equation, let's conserve angular momentum. And what do we conserve angular momentum about? Now the most convenient point is to take the center of mass of the rod itself, or more specifically, we'll take a point that's attached to the ground but is on the center of mass of the rod. So what I mean is, before collision, it's the point we are taking an axis that's passing through the center of mass of the rod. Now after collision, the rod will move, but the axis will not move because the axis is stuck to the ground. Okay, so that is the axis about which we are conserving angular momentum. All right. So what will be the angular momentum initially? Well, it will be just the angular momentum of the ball, and that will be equal to mv into L by 2, because this distance from here to here will be L by 2, right? So it will be mv into L by 2. This is the initial angular momentum. The final angular momentum will be the angular momentum after collision. So what will be the angular momentum of the ball after collision? That will be the mass of the ball into the speed of the ball, which is equal to VCM plus omega L by 2, right? This is the speed of the ball into L by 2. So this is the total angular momentum of the ball. What about the angular momentum of the rod? Well, that will be equal to, let's say, I omega. I will be equal to ml squared by 12. So we have ml squared by 12. This is the formula for the moment of inertia of a rod about the center of mass into omega. But this is not complete. We also need to add the angular momentum of the center of mass of the rod with respect to that axis. That axis, let's say, let me draw that axis over here. So let's say it's somewhere over here, right? It's a line passing through the paper, just very close to the center of mass, right? So about this axis, the angular momentum of the rod will be the angular momentum about the center of mass plus the angular momentum of the center of mass about this axis. But since we are assuming it's very close, and also it's pretty obvious that the velocity of the center of mass is passing through, right, through that axis, then therefore the angular momentum of the center of mass with respect to that axis will be 0. So we don't need to add that term. So this is the final angular momentum, right, of all the bodies. Now if I simplify this, we get m omega L squared by 4 plus m omega L squared by So we get to four omega, right? So this will become 3, 2. So we get 3v equals 3vcm plus 2 omega L. So this is your second equation. So now, if you look at our two equations, we have two equations with two variables. The variables are VCM and omega. So we have to solve these equations for that. Let's figure out the quickest way to solve this. If I multiply the first equation with minus 2, then I get minus 4v equals minus 8 VCM minus 2 omega L. And this, if I add it to our second equation, let me do this over here. So minus 4v equals minus 8 VCM minus 2 omega L. Second equation is 3vCM plus 2 omega L. If I add this, I get minus v equals minus 5 VCM, right? Okay, or VCM is equal to v by 5. Yep. So this is one value that we get. So the velocity of center of mass of the rod after collision is v by 5. But what do we need to find? We need to find the speed of the ball, which means we need to find omega. Let's calculate omega. If I substitute this value over here, 3v is equal to 3v by 5 plus 2 omega L L by 15 12v by 5 equals to omega L. Omega equals 6v by 5L. So this is the value of omega. But this still doesn't give us the final answer. The final answer, which is the speed of the ball with respect to the ground, will be, let's say whatever, v dash will be equal to VCM plus omega into L by 2. Yeah. So this will be equal to v by 5 plus 6v by 5L into L by 2 this will be 4v by 5. So the final answer will be equal to 4v by 5.
For more videos and live lectures on the JEE, click on the subscribe button now.